Welcome to this video on a numerical solution method for an ordinary differential equation. And the method that we will look at in this video is Euler's explicit method, so that by the end of this video you will be able to solve an ODE using that method. Now here's a recap of the general solution procedure that we have to apply to solve a first order ODE. dy dx is equal to f of x and y. We find the new independent variable by adding the constant step size h. And we find the new dependent variable y sub I plus 1, knowing the current value of the dependent variable y sub I, by adding a slope times the step size h. And the slope is simply the integral of dy dx, so the right-hand side of the ODE, over the interval from xi to xi plus 1 divided by the step size. So it's the average slope, the average right-hand side on the interval from xi to xi plus 1. So for a numerical solution technique, all we need is a way to calculate this slope, right? That's the key thing of solving numerically an ODE. How do we solve this integral that appears in the numerator? Well, it's an integral, right? So let's just use some of our numerical techniques to evaluate integrals. And the simplest one we had was the rectangle method. So let's evaluate this interval from xi to xi plus 1 of dy dx. Let's evaluate this using the rectangle method. Okay, so rectangle method applied to this. What is dy dx? Well, dy dx is the right-hand side of the ODE that must be given to us, this f of x and y. So we have to integrate from xi to xi plus 1, f of x and y dx. We use rectangle method, which means that the height of the rectangle is the function, the integrand, evaluated at the left bound, which would be xi and the corresponding yi, so f of xi yi, times the width of the interval, which is xi plus 1 minus xi. Xi plus 1 minus xi, if we have these points equally spaced, that would just be h. So the integral is just the function evaluated at xi yi times h. Okay, let's use this and plug it into the definition of the slope. So the slope is simply this integral, which is f of xi yi times h, divided by the h. So the h cancels, and the average slope, this slope that we need to find the new solution variable yi plus 1, is therefore simply f of xi yi. So the function f evaluated at my known values of the dependent and independent variable. So let's plug this into the equation, which means that the new dependent variable yi plus 1 is equal to the old value yi plus the slope being f of xi yi times now the step size h. And that is Euler's explicit method. It's the recipe to calculate the new value of the dependent variable, knowing the value of the dependent and independent variable at grid point I. Now, there's another way of getting this particular formula. Instead of using integration, I can also use finite differences. How? Well, let's use one of our finite difference formulas to approximate the derivative dy dx on the left-hand side. And we're going to use forward differences for this. So if I approximate dy dx using forward differences, dy dx at xi yi would be equal to yi plus 1 minus yi divided by xi plus 1 minus xi. And that then, xi plus 1 minus xi is equal to h, is simply yi plus 1 minus yi divided by h. And that is equal to the right-hand side evaluated at xi yi, so f at xi yi. Now I can take this equation and solve it for yi plus 1, and I get again yi plus 1 is equal to yi plus f evaluated at xi yi times h, which is the same formula that we obtained when we approximated the integral in the slope formula using the rectangle method. Now, because of the use of forward differences, this method is also sometimes called forward Euler and also, of course, called Euler's explicit method. Okay, so this is the solution approach, right? yi plus 1 is equal to yi plus f of xi yi times h. Now let's look at a geometric interpretation of this, right? So what does that geometrically mean? Well, it means that we have our solution at xi and yi, and we want to obtain the solution at the neighboring point xi plus 1. We want to know what is the yi plus 1. What this formula tells us is that we are going to use as the slope at the grid point xi, yi. We're going to use that slope of that blue line here as an approximation to the average slope on this interval. So if we follow this straight line of the slope for a distance of h, we will find the new solution variable yi plus 1. Now, which obviously has an error because the slope at the currently known value xi, yi is not equal to the average slope over this interval, but it's an approximation. Okay, so let's do an example. Let's solve the following ODE here. dy dx is equal to 1/10 x times y plus x, with the constraint that y at x equal to 0 has to be equal to 1. And I want to solve this on the interval of the independent variable x from 0 to 3 with a constant step size of h equal to 1 using Euler's explicit method, which is given up here again. Okay, so let's start with the constraint that the problem tells me. Constraint. The constraint was that x1, my first x value, is equal to 0. And my y value there, y1, is equal to 1. So let me make a table over here where I'm just writing in the first column the sub-index value for I, right? The first value here is at I equal to 1. Put a 1 in here, a 1. And I'm just going to write now the x values and the y values for I equal to 1. So the x value is 0 and the y value is 1. Okay, so now I'm going to use these update formulas, right? And I'm going to use them for my known value at I equal to 1. So I is equal to 1. And these formulas now tell me that x2 is equal to x1 plus h. But the h is equal to 1, right? So let's just plug in the values that we have. The x1, this x1 here is 0. And the h is given in the problem statement that is equal to 1. So we have here plus 1. And the x1 was 0. So the x2 value is 1. So let me write this in here. For if I is equal to 2, the x is going to be equal to 1. Okay, then I have the formula for y2. So y2 is equal to y1 plus f of x1, y1. So x1, comma y1 times h. Okay, so let's write what f is. Well, f has to be here, this right-hand side of the ODE. If I isolate dy dx, the first derivative on the left-hand side, then this entire thing here is f. So this is f of x and y. Okay, so let's plug in some values. So y1 is equal to 1. Let me just mark these here. Right, that's my y1. I'm going to use here and here. I had my x1, that's the yellow one that I have to use in the function over here, and my h was equal to 1. So I have 1 plus f which is 1/10 times x1, x1 was 0, times y1 is 1, plus the x1, that's my f, times the 1, which is the h. Well, let me color where these values came from. So the x1 was 0, that's used here and here, right? That's this value and this value. And then the y1, which is the 1, it's this value, that's the 1 over there and up here. Okay, so let's do the math on this. That first part here is 0 plus 0 plus 0. All of that is 0, so the end result of that is still 1. So we have a y2 that is equal to 1. Okay, I need to solve this all the way to the interval from 0 to 3. So I have the solution at 0. That was my initial constraint. I now have the solution at x equal to 1. And I have to go all the way to x equal to 3. So let's keep on going then. For I equal to 2, I have x3 is equal to x2 plus h, which is 1 plus 1, which is equal to 2. So if I is 3, x is 2. And my y3 is equal to my y2 plus f of x2 comma y2 times h. So that's equal to, let me just write this out in the long form at least once. So y2 plus 1/10 x2 times y2 plus x2 times h. And now let's substitute in the values. So the values here are these here, the x2 and the y2. Both of them are 1. So 1 plus 1/10 times 1 times 1 plus 1 times the h, which is 1 as well. So that means in here we have 1 times 1, it's 1/10 plus 1 is 1.1. 1.1 times 1 is 1.1 plus 1 is 2.1. So this is 2.1. That is the y value at I equal to 3, 2.1. And then we need to do a third step to reach x equal to 3. So I equal to 3. We have x4 is equal to x3 plus h. That's 2 plus 1, that's equal to 3. So if I is equal to 4, x is equal to 3. And the y4, using Euler's explicit method, Euler, so y4 is equal to y3 plus f of x3 y3 times h. So that's y3 plus 1/10 x3 times y3 plus x3 times h. Let's substitute in the values. The values for x is 2, y is 2.1. So I have y3 that is 2.1 plus 1/10 times x3, that's 2, times y3, that's 2.1, plus x3, that's 2, and the entire thing times h, which is equal to 1. Okay, so we have 2.1 plus, let's look over here, that's 2 times 2.1, that is 4.2 divided by 10, that's 0.42 plus 2, so that's 2.42 plus 2.42. And 2.1 plus 2.42 is 4.52. So the y value is 4.52. And now my solution, my numerical solution to this ODE is given here in this table format, right? The solution, numerical solution, is a set of discrete data pairs. I equal to 1, the data pair is 0, 1. At I equal to 2, the data pair is 1, 1. At I equal to 3, the data pair is 2, 2.1. At I equal to 4, the data pair is 3 and 4.52. That makes up the numerical solution to this ODE found with Euler's explicit method. Thank you for watching.